In set theory, a null set N(H) is a set that can be covered by uncountable union of intervals of arbitrarily small total length. The notion of null set in set theory anticipates the development of Lebesgue measure since a null set necessarily has measure 0. Definition: suppose A is a subset of the real line R such that where the UN are intervals and U is the length of U, then A is a null set. In terminology of mathematical analysis, this definition requires that there be a sequence of open covers of A for which the limit of the lengths of the covers is 0. Null sets include all finite sets, all countable sets, and even some uncountable sets such as the Cantor set. Properties: the empty set is always a null set. More generally, any countable union of null sets is null. Any measurable subset of a null set is itself a null set. Together, these facts show that the M null sets of X form a sigma ideal on X. Similarly, the measurable M null sets form a sigma ideal of the sigma algebra of measurable sets. Thus, null sets may be interpreted as negligible sets, defining a notion of almost everywhere. Lebesgue measure: the Lebesgue measure is the standard way of assigning a length, area or volume to subsets of Euclidean space. A subset N of A has null Lebesgue measure and is considered to be a null set in if and only if, given any positive number I micron, there is a sequence N of intervals in R such that N is contained in the union of the N and the total length of the union is less than I micron. This condition can be generalized to Rn, using n cubes instead of intervals. In fact, the idea can be made to make sense on any differentiable manifold, even if there is no Lebesgue measure there. For instance, with respect to Rn, all one-point sets are null, and therefore all countable sets are null. In particular, the set Q of rational numbers is a null set, despite being dense in R. The standard construction of the Cantor set is an example of a null uncountable set in R. However, other constructions are possible which assign the Cantor set any measure whatsoever. All the subsets of Rn whose dimension is smaller than n have null Lebesgue measure in Rn. For instance, straight lines or circles are null sets in R2. Sard's lemma: the set of critical values of a smooth function has measure 0. If I is Lebesgue measure for R and I euro is Lebesgue measure for R2, then the product measure IXI equals I euro. In terms of null sets, the following equivalence has been styled a Fubini's theorem, for R SHA2 and uses, null sets play a key role in the definition of the Lebesgue integral. If functions f and g are equal except on a null set, then f is integrable if and only if g is, and their integrals are equal. A measure in which all subsets of null sets are measurable is complete. Any non-complete measure can be completed to form a complete measure by asserting that subsets of null sets have measure 0. Lebesgue measure is an example of a complete measure. In some constructions, it's defined as the completion of a non-complete Borel measure. Equals a subset of the Cantor set which is not Borel measurable equals, the Borel measure is not complete. One simple construction is to start with the standard Cantor set K, which is closed hence Borel measurable, and which is measure 0, and to find a subset F of K which is not Borel measurable. First, we have to know that every set of positive measure contains a non-measurable subset. Let F be the Cantor function, a continuous function which is locally constant on Kc, and monotonically increasing on 0, 1, with f 0 equals 0 and f 1 equals 1. Obviously, f Kc is countable, since it contains 1 point per component of Kc. Hence f Kc has measure 0, so f k has measure 1. We need a strictly monotonic function, so consider g x equals f x plus x. Since g x is strictly monotonic and continuous, it is a homeomorphism. Furthermore, g k has measure 1. Let E(g, k) be non-measurable, and let f equals Ga1, e. Because g is injective, we have that f(k), and so f is a null set. However, if it were Borel measurable, then g f would also be Borel measurable equals a 1, f is the primage of f through the continuous function h equals Ga1. Therefore, f is a null, but non-Borel measurable set. Haar null, in a separable Banach space, the group operation moves any subset A-X to the translates A plus X for any XLX. When there is a probability measure I1/4 on the I-Florin algebra of Borel subsets of X, such that for all X, I1/4, A plus X, equals 0, then A is a Haar null set. The term refers to the null invariance of the measures of translates, associating it with the complete invariance found with Haar measure. Some algebraic properties of topological groups have been related to the size of subsets and Haar null sets. Haar null sets have been used to in Polish groups to show that when A is not a megaset then or Euro-1A contains the identity element. This property is named for Hugo Steinhaus since it is the conclusion of the Steinhaus theorem. See also, Cantor function, measure, empty set. References: Merck-Kapinski and Hardkop measure, integral and probability, page 16, Springer ISBN 1-85233-781-8. Frank Jones Lebesgue integration on Euclidean spaces, page 107, Jones and Bartlett ISBN 0-86720-203-3. John C. Oxtoby measure and category, page 3, Springer Verlag ISBN 0-387-05349-2.